So now we're going to move on from points, lines, and planes into our understanding of triangles. A geometric figure that is identified as closed is going to be a geometric figure that I start at one point, I trace the entire figure, and I finish at that same point that I started at. So there's no breaks or gaps in the figure, and that's why we say that it's closed. A triangle is closed. It has 3 sides and 3 angles. And it also has 3 vertices, which are basically those connecting corners of the triangle. Triangles are named with the 3 labels for each vertex. So I could call this ABC. I could call it ACB. I could call it BCA. The order does not matter as long as it encompasses each measure of the vertex. Triangles have several different names and classifications. An isosceles triangle has 2 sides with the same length. An equilateral triangle has 3 sides with the same length. A scalene triangle has no sides with the same length. Now what's interesting is that an equilateral triangle has 3 sides that are equal, and we use the equilateral so that we should be able to pull out equilateral. Isosceles is going to be a little different for students because that doesn't really make sense for a prefix for them. So that's going to be one that you're just kind of going to have to drill into, that an isosceles triangle has 2 equal sides. I can also classify triangles by their angles. If it's an acute triangle, all of its angles are less than 90. If it's a right triangle, one angle measures exactly 90 degrees. And if it's an obtuse triangle, one angle is greater than 90 but still less than 180. So if I'm looking at these 3 different types of triangles, in angle A, I can see that we already have an obtuse angle because 120 is greater than 90. So triangle A is going to be an obtuse triangle. In triangle B, I can see that it has 3 congruent sides, so it's going to be equilateral. I can also see from looking at the angles that none of them are going to be over 90 degrees. So it is both equilateral and acute. And then in part C, I have one angle that's exactly 90 degrees. Something that's of worth to note is that if I add all the angles up in a triangle, they are going to add up to be 180 degrees, which is the same value as our supplementary angle. I can draw any formation of a triangle, but I will never be able to draw one to get that it's going to be greater than 180 degrees. There's just no way to do this. If I want to solve for an angle in the triangle, I have to know what 2 of the angles equal. I must know at least 2 in order to find the third. So if 40 plus 40 plus angle C equals 180, then I can do 180 minus 40 to get 100 degrees, and angle C measures 100 degrees. So it's a rather straightforward problem as long as you remember that property of 180 degrees in a triangle. The Pythagorean Theorem is a very popular theorem, and it's been proven true many times over with deductive reasoning. It is very specific to a right triangle. If you do not have a right triangle, you cannot use it. The hypotenuse of a right triangle is going to be the longest side, which is also opposite of the right angle. I refer to the 2 other parts of the triangle as just plain old legs. What the Pythagorean theorem tells me is if I square the values of the legs and I add them together, that is going to be the same as squaring the hypotenuse. So what does that actually look like in practice? So for the right triangle shown in part A, I want to find the length of A. Now, if I look at that right angle, the value across from it is 30. So 30 is my hypotenuse. A and 24 are my legs. So I'm going to do A squared plus B squared equals C squared, where A and B are legs. I replace B with 24 and the hypotenuse with 30. Then I have to use my calculator to square those values, or I could subtract 24 squared and type this entire statement into my calculator, which gives me 324. A lot of students make the mistake of stopping at 324 and saying, oh, I'm done. I have the answer. It's 324. But that's what A squared equals. In order to find what A equals, you have to take the square root of 324 to get 18. Now, where should you round? You should round to the second decimal place if you have a rounding situation. In part C, if the triangle is right, then it should satisfy the Pythagorean theorem. So if I go back to part C, which of these triangles is a right triangle? So I'm going to test it out. I'm going to test out that the longest side is the hypotenuse, so 13 would be the hypotenuse, or the square root of 41. Those would have to be the hypotenuses because they're the longest sides. So I'm going to set it up with taking the legs, squaring them, and seeing if it equals the hypotenuse squared. In this case, it does not for the first triangle. And the second triangle, it is a true statement. So I know the second triangle is going to be a right triangle. Another example of this is when I'm taking that larger acute triangle and I'm splitting it into two triangles. It forms two right triangles in that case, and I bisected 12 according to hitting it at the halfway mark. So if I want to find the length of the diagonal beam, which would be the question mark in the problem, I'm going to need to do some math. So I'm going to use the Pythagorean theorem because the line that I'm trying to find where the question mark is the hypotenuse. So I'm going to have my leg of 6 squared plus my leg of 3 squared, and that's going to give me 9 plus 36, which is 45. A lot of times you will not get whole numbers, and that's okay. The square root of 45 from your calculator is about 6.7 feet. Similar triangles are not right triangles, but they are scale factors of one another. So think about architectural drawings. I can't draw something life-size. I can't draw a skyscraper in a life-size model, or a house even in a life-size model. So I can say, well, I'm going to scale it down using a certain scale, and so maybe an inch on the paper is really like a mile. That's how similar triangles are utilized. It's very similar to a map legend. If two triangles are similar, then their angles are equal. So if I tell you these two triangles are similar, the measure of A is 40, what is the measure of A prime? The answer is 40, because the angles that correspond have the same values. Now the sides are not going to be equal. They are going to be approximately similar. To find how similar they are, I do what I call a scale factor. So I would say, okay, this is my 10, this is 30, those are corresponding lengths. So my scale factor is 10 divided by its corresponding leg of 30, which is 1/3. If they are truly similar triangles, when you apply that to 6 divided by 18 and 4 divided by 12, you should get the same value. So if it's telling you to prove that two triangles are similar, you're going to prove that by finding the same scale factor for each side of the triangle. Here's another example. If the triangles are similar, find the length of BC. So how am I going to do that? I'm going to set up a proportion. I know that AB is 8 and A prime B prime is 6. Those are corresponding legs, so I'm going to do 8 over 6. Now, I don't know what BC is, or BC prime is, but I do know that BC is 12. So I'm going to fill in BC has to be at the top because it corresponds to AB. And then I'm going to fill in my numbers, cross multiply. So 8 times x, 6 times 12 is 8x equals 72. Then I divide both sides by 8, and I get that x is going to be 9. Now, how do I use similar triangles in real world situations? Well, in this problem, I have a tree casting a shadow, and then I have a person casting a shadow. So if I kind of sketch this out, very rough sketch, this is what it would look like. And then I'm going to label each part of my sketch. So why are these two similar? Well, both of the diagrams have a right angle, so they're both meeting the ground at a 90-degree angle, so that's intriguing. The sun creates the same angle on the ground for both diagrams, so I know that my angles are going to be equal. And if two triangles have the same measurements for all three angles that correspond to one another, then they are going to be similar by definition. So to set up the similarity, I'm going to define the height of the person that they gave me, divide that by their shadow, then the height of the tree, and the length of the tree's shadow. I'm then going to cross multiply 5 times x and 5 and 10/12 times 12. Then I divide both sides by 5, and that is how I arrived at 14.